Hello all, this is Shashikant here again. Today I will be presenting my work, a data-driven frequency scaling approach for deadline-aware energy efficient scheduling on graphics processing units. This work was accepted as part of CCGrid 2020. In this talk, I will briefly introduce about this problem domain. Then I will explain about the motivation for this study. Then I will present our system model as well as our solution approach. Then I will show a few of the results which we obtained from this paper. Then I will conclude the paper with the observations we have found in this study. Graphic processing units have been used for many decades, mainly for accelerating the graphics in computers. However, recently they have been used for general purpose computations, usually called as GPUs. Thanks to their single instruction multiple data stream architecture, which is beneficial for a large number of applications that demand parallelism. Applications like HPC domains, where massive scientific applications do require a parallelism, and most of AI or ML workloads in the training process, they do need to run workloads in a parallel, as well as even applications like crypto mining have been seeing massive usage of GPUs. As the applications domain are increasing for GPUs, they have been found more places in cloud data centers as well as HPC data centers. Despite their increased usage, power consumption has been their main bottleneck for building hyperscale GPU systems. A single GPU consumes power in the order of 200 to 300 watts, and we have seen that a blade server will equip multiple GPUs within a server to meet the increased usage as well as the workload demand. On the other hand, GPU workloads have become more sensitive to their quality of service, which often require faster execution, thus spending a large amount of power in their execution. There have been different methods to address the power consumption of GPUs with a different abstraction layer and resource management techniques. However, at the lowest abstraction layer, power consumption can be addressed with two components. One is a static power, another one is a dynamic power. Static power, it mainly deals with the leakage in the circuit, which can be addressed with a better circuit design, as well as the low power management or sleep state management of processors. The majority of power consumption in GPUs comes from the dynamic power, which is regulated with a technique called dynamic voltage frequency scaling. Unlike CPUs, GPUs have two main components for frequency. One is the core frequency, which regulates streaming multiprocessors, including registers, texture, cache, whereas the memory frequency, which regulates the bandwidth to the DRAM. Some GPUs have multiple frequency domains for core as well as the memory. For example, NVIDIA GTX 980 has total 87 core frequencies and 4 memory frequencies, and the combination of both together, we can set around 266 possible frequency combination. It is important to note that not all memory frequencies supports all the core frequencies. Nevertheless, we still have hundreds of possible frequency domains in our graphic processing units. And particular set of combination of frequency can be set using application layer library, something called NVML, which is provided by most of the vendors. We did study how exactly the DVFS works for different applications considering the power and time. What we found is the common expectation is always when we increase the frequency, the power consumption will increase. Obviously, the usage of circuitry would result in higher power consumption, and it would reduce the execution time as the clock will be running at a higher speed, which is true for some of the application, as in this case B. However, there are some applications that do not follow any of the linear expectations what we usually like to find in DVFS. For example, consider the application case A. Increasing the frequency is decreasing the time. However, there is no linear behavior with the power consumption. And similarly, in application C, increasing the frequency is increasing the power consumption, but it has almost non-linear or no linear behavior with respect to the execution time. In the worst case, even increasing the frequency may have negative effect in the execution time of some of the applications. We also seen few applications where there is no correlation between power and execution time in a linear manner when we increase the frequency from lower frequency domain to the higher frequency domain. This is mostly to deal with the resource usage characteristics of individual application that may have a different kernels and different response for their execution as well as power consumption. So the objective of this study is to reduce the energy consumption of GPU by efficiently scaling the frequencies in application execution. So to achieve this, we propose our system model consisting of two parts. One is an ML prediction models, and other one is using this ML prediction model. We propose a scheduling algorithm that finds a best suitable schedule sequence as well as scales the frequency in runtime to match the application requirements. As I explained earlier, the existing solutions to scale the frequency either go with the linear approach or use the simple heuristics that fail to identify the workload characteristics and suitably scale the application frequency in their execution. Our system model consists of two parts. One is a data-driven modeling, which is mainly about to predict energy and execution time based on the profile data. And once we build these models, we use it for resource management aspect. In this particular study, we use it for scheduling. In this scheduling part, we take the QoS requirement, that is deadline, as and when application comes, a scheduler would interact with these prediction models and configure the application's required configuration of their frequency and execute their application in runtime. So how exactly we are doing this prediction modeling? So prediction modeling requires initially profiling. We do collect three components of data. First one is obviously the profiler, where we run all the benchmarking application on different frequency and collect all the resource usage footprints. Then the corresponding energy and execution data. Then that particular frequency configuration which we have been running this profiler. All these three components acts as a training data. Then we build the models to predict energy as well as execution time. So going over what benchmarks we use in this study, our study included 12 total applications from two benchmarks, popular benchmarks in GPUs, that is Polybench and Rudinia. These applications, some of comes from different application domains, including medical imaging or biological simulation, or the other set of applications consist of basic mathematical computation, for example, covariance computation or correlation computation. Remember, all of these basic computation are also part of all the AI, ML, or HPC workload, where they do execute this basic mathematical computation millions of times in their training process. For example, matrix transpose, matrix multiplication, vector multiplication, all of these are done in different applications. Okay, so we have used European Grid 5K and Tesla P100 GPU as a test bed, and the profiler we use NVPro, which is an NVIDIA profiler that can be used to run an application and collect all the resource footprint and all the features of a particular GPU. Each run will give around 120 features, including all the readings about different registers, memory, and all the counters that present in a particular GPU. As we wanted to predict execution time as well as the power consumption, it is no brainer that we have to go with the regression models. So we did test different regression models, including linear regression, lasso, linear regression, XGBoost, and CADBoost. And we built two separate models. One is for energy execution, energy prediction, and other one is execution time prediction. So these are the results of predictive modeling. And based on our experiments, we found that CADBoost works better for both energy prediction as well as time prediction. Part of the reason is out of 120 features, we do have few of categorical features, and Cat Boost is primarily designed to efficiently transform the categorical features for regression purposes. And looking at the RMSE values for energy prediction, it is 0.38, and for time prediction, it's 0.05, which also signifies there is more non-linearity with respect to energy consumption compared to the compared to the time prediction. Out of all those 120 features we collected, to identify which are those features that actually contribute to our accurate prediction in regard to energy and time, then we did a future importance study to understand that particular aspect. So this result show individual features and the x-axis, and the y-axis shows the future importance score, which signifies what will be the RMSE values with or without this particular feature. Based on this, we found that 20 features are good enough to accurately predict the execution as well as the time. And these results also show that for time prediction models, features like related to IO, like DRAM write transactions, are more significant than energy prediction models, which signifies IO related features are more dominant in predicting the time compared to the energy models. Once we build the prediction models, then one can use it for different resource management techniques, and we have used it for our scheduling. Our scheduling mainly consists of 4 components. That is, what we built a runtime predictor, which can inference using the trained models. And once we predict the accurate frequency, we can configure that frequency, then execute our application. We also use for correlation, we also use a clustering to avoid training again and again for different applications that may come in the future. The more detail about this is also present in the paper. Okay, so our main objective of this study is, given a number of applications, each one have their own application arrival time as well as the deadline, which we consider as a QoS parameter here. If we have n number of such application and each application follows their own power and execution time curve, some may have the linear curve, which is expected. For example, increasing the power will decrease the execution time. But this may not be true for all the applications. So our idea is to find that optimal point where, given an application, what would be that frequency where we have lowest power as well as the fastest execution. So our goal is to reduce the overall power consumption of GPUs while scheduling this n number of applications. We propose a scheduling algorithm. Basically, it sorts all the applications based on the arrival job, based on the deadline. If that particular application has arrived into the system, we do predict what would be its execution time as well as the power consumption over different clock sets. Then we select particular frequency that meets the deadline, as well as it has the lowest power, and we use the same NVML library to configure the system and execute that application. And remember, we are not training this particular application and using that exact trained model. We do correlate with the existing trained knowledge database. Then once we get that correlated data, then we use that application that mostly correlates with the new application that is arriving in the system, and we use the training models of that particular application that has high correlation based on clustering. Okay, so going over the results of the scheduling part, this particular graph shows on the x-axis different applications, and the y-axis shows the average power consumption. Based on the result, you can see that our approach, that is DDVFS, consumes the lowest power in all instances compared to the baselines, that is max clock and default clock, that NVIDIA uses in their application execution. And in total, proposed solution DDVFS consumes around 15.07% less energy compared to the best performing method, that is default clock policy. To identify how exactly the frequency is scaling in our system, while max clock and default clock statically set either a default value or the maximum possible frequency to increase the performance of an application, whereas our application, based on the deadline requirement, scales the frequency to achieve the deadline as well as to reduce the power consumption. We can see that if the application deadline is tighter, it can increase the frequency. But the good thing to note about is even the highest frequency of our approach is still lowest than the default clock in this particular set of applications. To see how it is performing with respect to deadline, this is a graph with normalized time. The red dots are deadlines and the green ones are the completion times of our DDVFS, and blue ones are the completion times of default clock, and this black one is completion times of max clock. As we can see, the DDVFS approach finishes its application execution well before the deadline, and in some cases well before the max clock, which is a surprising result in our case, which shows that not all applications will perform better if we just increase the clocks. Some applications perform better even at the lower clock based on their resource usage characteristics. To analyze how the performance of our prediction models working in runtime, so we did predict initially in our scheduling what would be a predicted power of this particular application, as well as what would be the predicted execution time. When we compared the result with predicted power and execution along with the actual power consumption and the execution time, we can see that our actual consumed power closely follows the predicted power curve, showing the feasibility of such prediction models in runtime. It is the same case with time model, where the actual time follows closely with the predicted time in our application execution, showing again the feasibility of our proposed models. To conclude my talk, application kernels in graphic processing units behave differently even with the same clock settings. This is mostly to do with their resource usage characteristics. Not all applications will perform better simply increasing the frequency of GPUs. And existing solutions like linear frequency scaling as well as heuristics are inefficient to accurately identify the frequency of an application, best frequency of an application. Whereas data-driven model helps to accurately model the frequency scaling. Not only they can be used for frequency scaling, data-driven models can also act as a feedback loop for different resource management techniques in cloud or HPC data centers, as well as the system architectures where one can see which particular set of application is contributing to the energy consumption based on their resource usage characteristics. So if you're interested more about the implementation aspect of this project, you could find the software repository on this URL. Thank you.